All right, here are the solutions all worked out by hand for the assignment that I gave you guys on Monday for 380 to 381 on those pages 2, 6, 8, 12, and 14. All right, so 2, 6, and 8, we were given the graphs. Let's take a look at these here. All right, one thing, I'm just going to go ahead and have the graph all the way down here, just to show you we could use symmetry to help us set this up. That way we're working with a 0. And within this, we have to use a little trig identity. So I set this up that, again, make sure that you have a is equal to. Don't just start off with an integral and not state what it's helping us find. So we could just double the integral from 0 to pi over 3, and then our upper curve is the 1/2 secant square t, and then our lower curve is the -4 sine square t. So we have the top curve minus the bottom curve here, and then I just went ahead and took care of the double negatives here. And then in order to help us take the antiderivative of sine squared t, we always want to use the cosine 2t identity to help us out with sine squared t or cosine squared t. So again, cosine 2t is equal to 1 minus 2 sine squared t. Solving it for sine squared t, we get 1/2 minus 1/2 cosine 2t. So what's going to work out nice is when we go ahead and distribute this 4, we no longer have fractions here. So again, this is all before we take the antiderivative. The antiderivative of secant squared t is just going to give us tangent t. So in the next step, we have, and feel free to pause this at any moment. So we have 1/2 tangent t plus 2t, and then this just becomes minus 2 or minus sine 2t, because if we were to take this derivative, we would get cosine 2t times 2. So because of that 2 that's out in front, we didn't need any other coefficient. And then we're going to evaluate this from 0 to pi over 3. And in doing that, you can see I have all the pi over 3's first, so this just became 2 pi over 3, even inside 2 pi over 3, and then all of these are zeros, even 2 times 0. I just left that as 0. So tangent of pi over 3, remember tangent is sine divided by cosine, so make sure you know your unit circle here. At pi over 3, we're at 60 degrees, so sine is going to be radical 3 over 2 divided by 1/2, so that just gives us a radical 3. So we get radical 3 over 2 plus 2 pi over 3 minus sine of 2 pi over 3. We're in the second quadrant, still up at like the 60-degree reference angle there. So we get minus radical 3 over 2 sine, still positive, and all these other values just give us 0. So now the radical 3 over 2's cancel. We're left with 2 times 2 pi over 3, which gives us 4 pi over 3 square units. All right, for number 6, again, we can use symmetry. We can't for number 8, though. Everything else seemed to be based off of symmetry here. So again, looking at the graph, we could double the integral from 0 to 1. Our upper curve is x squared. Our lower curve is minus 2x to the 4th. So again, when we subtract, it will become a plus 2x to the 4th. This one, I feel, was a little simple compared to some of the other problems that we went into, as far as not as many steps involved with the antiderivatives here. No trig identity substitutions were needed as well. All right, so just look at the steps. Again, evaluating from 0 to 1, we do get involved with fractions. So here we end up with 22/15 square units. All right, now in number 8, this is where we could set this up in a couple different ways, because we're actually dividing our graph, because at one point the graphs change which one is on top, which one is on the bottom, or just the upper curve that's here. So it changes right at x equals 1. Notice we're going from our curve just down to the x-axis here, where the blue curve y equals x squared is our upper curve, and then it switches after that. And I did just rewrite this, solve for x or solve for y in terms of x here. So there were two ways we could set this up. We could first go from 0 to 1, where we're just looking at the difference between x squared and then the line y equals 0, so we really don't need the minus 0 up here. And then we can set up the second integral, where the line y equals negative x plus 2 is our curve. Or if you notice, it makes a nice triangle, so these are both good ways to do this. The second approach, less writing this way, and just going through these steps here, where we're just getting the antiderivative of x cubed over 3, evaluating that from 0 to 1, and then we just get plus 1/2. Both of these, though, I've worked them out both ways, that you can see we get 5, 6 square units. All right, for number 12, actually for 12 and 14, it's helpful to find the points of intersection, and then for some of these to graph, we may need to find the x-intercepts as well, which is what I did for y equals 2x minus x squared. First, I found the x values of the points of intersection here. So I set them equal to each other, found that they intersect when x is -1 and 3. Now I know y equals 2x minus x squared is quadratic. It's a parabola that opens down. So I also went and found the x-intercepts were at 0 and 2. So I plotted those first. I'm just going to go ahead and do that. So what I did was I plotted the x-intercepts here. And then I know based on symmetry, I know my vertex is going to occur halfway in between those. So when x is 1, I just substituted the back in. Y is 1, so I found my vertex this way. Now a is -1, so I know if I count over 1, I'm counting down 1. If I count over 2, and I numbered every 2 blocks as 1 unit. So if I count over 2, I'm going down 4. So here I had 2 other points that I plotted. And then very simple, I have the line y equals -3, so we could clearly see this here. So maybe doing what I have up here in red wasn't necessary, but what I did in purple is a quicker way to graph y equals 2x minus x squared. So I can't use symmetry here. So I would just set up the integral from -1 to 3. My upper curve stays as the upper curve the entire time. So I have 2x minus x squared first, minus the -3 becomes +3. Take the antiderivative of that. Carefully watch your signs here, but you should be getting 10 2/3 or 30 2/3 square units. I know number 14 was a lot of fun to graph here, so I did the same thing. I actually picked some other points for y equals x to the 4th minus 4x squared plus 4 to help us. I made a little table of values here. I can get my screen to come down. All right, it's working now. All right, so it was working. There we go. All right, so again, I set the two equations equal to each other. I found there's actually 4 points of intersection. And if you wanted just to double check on your calculator, that's fine too, but it is possible to take our time to figure this out by hand as well. So I have 4 points of intersection. But before I even graphed all of this, I know it looks like there's a lot going on here. Let me show you what I went through to come up with this. So I also found the x-intercepts of the y equals x to the 4th minus 4x squared plus 4. And I noticed that they occur at plus or minus radical 2. And then I just picked some other values as well. So I started at 0. And the y-intercept of the first graph, what I have here in purple, is 0, 4. So the y-intercept is 4. Then at the points of intersection, that's all I really cared about. I know both of these, since they're even functions, they're going to have symmetry with respect to the y-axis. But also to figure out the points here, I just chose 0, and then I chose where they were the points of intersection. So when x is 1, y is 1. When x is 2, y is 4. Same when they're -1 and -2. So that allowed me to get these 4 points up here. And going back to what I meant with symmetric, that they were both opening up as well, being even functions. So I had the point here, -2, 4. Here is the x-intercept of negative radical 2. And then when x is -1, y is 1. Up here at 0, 4. Same thing at 1, 1. Here's my other x-intercept, and then up here as well. And then it's sort of stretched out. Notice how I have my x-axis numbered. And then y equals x squared. Again, we have 0, 1, 1, 2, 4. So we have the points of intersection. So we actually have 3 areas that we're trying to find, but we can use symmetry to our advantage here. That way we're not writing out 3 different integrals, but 2. So for 0 to 1, the purple curve, so the y equals x squared minus x to the 4th minus 4x squared plus 4 is the upper curve from 0 to 1. But after 1, it switches where x squared is the upper curve. So right now, just look at the setup of both of these integrals here. And carefully watch your signs. That's just what I'm going through with the rest of this. I can combine my like terms in the first one here. I need to subtract all of these, combine the like terms, and then the rest is just careful calculations. So take a look at each step. I know we get involved with a lot of fractions, but all of these numbers simplify to just an 8 squared units. All right, so I'll also post this as a PDF. That way you don't have to keep going back and forth through the video and pausing each step. But as always, guys, take care, and let me know if you have any questions.